We will now consider a similar exercise on the cross method. We have a beam like this. It is subjected to a concentrated load P on beam AB and to a uniform distributed load on beam BC and CD. The uniform load is Q, and the load P is taken to be equal to Q by L. So when we apply the cross method, we have to consider the fixed end moments coming from the structural scheme in which we lock the rotations in node B and node C. Well, actually these rotations are not the unique displacements we can have on these structures, since we can also have a rotation in node D. Here we add the additional restraints only in node B and C, since the structural scheme of beam CD loaded with a uniform distributed load is known. So by only adding the additional restraints in node B and C, we are able to calculate the fixed end moments of this structural scheme, considering the uniform distributed load on beam BC and CD and the concentrated load on beam AB. So, you know that the bending moment diagrams is this one. And the values of the fixed end moments are Q L squared over 8. In this case, the bending moment is P L over 8. P is equal to QL, so the final results for the bending moment is QL squared over 8 on both sides. Then on beam BC, we have two bending moments at the support equal to QL squared over 12. And on beam CD, we have a bending moment in C equal to QL squared over 8. Well, the length of the beams, of course, is L. L. Well, we now have to calculate the distribution factors. So we have rho BA is equal to 4R, which is the flexural stiffness of beam BA when we want a unitary rotation on B, over 4R, the rotational stiffness of beam BA, plus 4R, which is the rotational stiffness of beam BC, equal to 0.5. Rho BA is also equal to rho BC, because the two beams converging in node B have the same rotational stiffness. The distribution factor rho BC instead is equal to 4R, that is the rotational stiffness of beam CB, over 4R plus 3R, where 3R is the rotational stiffness of beam CD. and it is equal to 0.571, while the distribution factor rho CD is equal to 3R over 4R plus 3R, that is 0.429. We'll write them here. And we are now ready to start with the iterative method. So this is the scheme for the cross method. We start by writing the first bending, which are the fixed end moments. So we have here minus 0.125. All the values I'll write here should be multiplied by Q L squared. So we have a first bending equal to minus 0.125 on node A. On node B, on the left, a positive bend equal to 0.125, which is the QL squared over 8 found before. On node B, on the right, we have a negative bending moment equal to 0.083, which is the QL squared over 12. On node C, the same value but positive, so 0.083. And on node C on the right, we have a first bending equal to minus 0.125. And on node D, the first bending is 0. So, we have to start from a node which is not balanced. So we will start from node B. We have to sum up the bending moment coming from the first phase, and then we have to distribute the resultant according to the distribution factors we have just calculated. So we obtain a second bending moment on B on the left equal to minus, since it has to be opposite with respect to the moments coming from the first step, minus 0.021, which is equal on the right. Now we have to consider the carryover factors in order to write the third bending moments, which are 1/2 with respect to the second. They have the same sign, so we have on node A minus 0.011. And the same thing for the third moment on node C. So minus 0.011. Okay, and now node B is balanced. We have now to consider on node C, we have to sum up all the bending that are present. So I have to sum up 0.083 minus 0.125 minus 0.011, and we have to distribute the resultant according to the distribution factors. So we obtain second bending moments positive and equal to 0.030 on the left, and 0.023 on the right. On beam CD, the distribution factors is 0, so we have no bending, no third moments on node D, while here we will have a third bending on node B on the right equal to 0.015. And now node C is balanced. Then we have an unbalanced moment on node B equal to 0.015. We distribute it and we obtain negative second bending moments equal to minus 0.008 on both sides. We consider the carryover factors and we obtain a third bending moment on node A equal to minus 0.004. The same thing on node C. And now node B is balanced. We consider node C and we distribute the moment equal to minus 0.004 and we obtain second bending moments equal to 0.002, well, on both sides. We have a third moment on B on the right equal to 0.001. Now node C is balanced and we stop here since the carryover bending moments is sufficiently small to be neglected. Well, now we have to sum up all the contributions. So we obtain on node A a bending equal to minus 0.14. Of course, all these results have to be multiplied by QL squared. Well, on node B on the left, we have to consider 0.096 as the final bending moment coming from the sum of the contributions previously calculated. On the right, we have negative bending equal to 0.096. Here on node C on the left, we have a bending equal to 0.10 positive, and on the right, a bending negative equal to minus 0.10. And on node D, we have a null bending moment. So, we can now check the equilibrium at node B and C, summing up the resultant for the bending moments on the right and on the left. And here in this case, we have that the equilibrium is respected, since we have 0 as the sum of the bendings coming from the left and on the right. So the final bending moment diagram is this one. where the values are 0.14 QL squared on node A, 0.096 QL squared on node B, and 0.10 on node C. QL squared, of course. This is our final bending moment diagram.